The next speaker is Roel Vernooij. Well, as you have seen, I think we have some sort of progression from engineers with huge experience, engineers which I would call myself young engineers, but already are engineers with about 15 years of experience, such as the latest ones. And now we have a younger engineer. Roel Vernooij is from in Arup. Arup is a very well-known engineering consultancy company. He did his bachelor in Amsterdam and then his master in Edinburgh. And he has been, he joined Arup in 2013, so he has about 2 years experience. And he has done quite already some work in large steel bridges in the Netherlands. And lately he has been working in a major project for a suspension bridge in the Netherlands. So you have the word, Roel.
Hello, I'm Roel Vernooij. I know Spanish people can't roll the R's, so it's okay. It's okay, don't worry. I'm a bridge engineer at Arup and almost 3 years experience now, so that's quite young. But I've been lucky enough to be involved in quite some interesting projects, and I hope to tell you something about those. So let's start. This is the bicycle bridge I designed. This is in Utrecht, where I'm from, so a local project, always nice. And it's a suspension bridge. It's about 110 meters span, and suspension bridges aren't very common in the Netherlands. We don't have very good soil, so the anchorages are usually a big problem and very expensive. Therefore, other bridge topologies are usually a lot cheaper and therefore the favorable choice. However, with bicycle and pedestrian bridges, the loading is less, and therefore you are a bit more flexible in the options you can choose. So we've been working together with architects to come to design, and all went well, quite smoothly to quite far in the process. And quick view of the model. It's asymmetric. The tower on the left is higher to represent the more offices and high-rise buildings on that side of the canal, while the tower on the right is shorter to represent the more houses and a bit more living area on the other side of the canal. It has inclined hangars, something we discussed with the architect. They really liked the inclined hangars, and they are good in some ways and bad in some other ways, just like all the decisions we have to make. The good way is that it makes it more stiff. There's a bit of shear transfer between the deck and the main cable, and that is overall a good aspect. There's fatigue problems that come with those as well, but because this is a pedestrian bridge, fatigue issues aren't that big of a deal, while when there's cars or trains on the bridge, it's a bigger impact. However, we were almost finished. We were in a good position. Some earlier sketches of the design at the earlier process. We ran into a problem, well, two actually, quite late in the design process. Basically, if there's a half loaded span, the main cable will deflect on one side and straighten on the other side, and it will shift a bit towards the loaded side. When you have straight hangers, this is not really a problem, but when you have V-shaped hangers like you see in the middle, one of them gets elongated and the other one gets shortened, and that means that one of the hangers will increase in force and the other one will decrease in force. And for us that meant some of the hangers would be tensionless, they would go slack, and that's a bad thing. It's a bit difficult to calculate the impact on the getting tension again on the connections. They might go like a guitar string and vibrate a lot when it happens. It might be a safety issue, and it's considered in general to be bad practice. This is a quick plot. The hanger configuration on the top with just the dead loads and the minimum hanger force, something we weren't that interested in until this time, is plotted below. As you can see, most of the hangers in the middle, where the effect of the displacement is the largest, would lose all their tension. That was a problem, and that needed to be solved. Another problem was the clashing of the hangers. They're all connected to the same main cable, or one of two main cables. And at the top, where the connections to the main cable are very close, the hangers are actual clashing. That was a problem we didn't really know how to solve. And at the bit lower points, they're not clashing per se, but they're really close. Something we wouldn't really like as well. You don't want the hangers to be slapping against each other during wind. But on the other hand, it is a suspension bridge. There will be a lot of movement when there's loading on the bridge, so they need to be able to move compared to each other. This was a really difficult detail, and we asked some people to say, hey, how would you want to solve this? And the answer we got was avoid, which was not the answer we were looking for quite that late in the design process. So we had a bad news conversation with the architects involved and also the clients. We had to go back to the drawing board, well, not completely, but we had to go back a few steps and change the design. While we were discussing different options, we were at the table with mostly engineers, and the engineers, when they got a problem, they go back to the known route, and that was straight hangers. I was like, yeah, all problems solved, easy, let's go home, finished. But the architect didn't really like that. They were happy with the inclined hangers. And not just the architect, it was also the city council who has already been made aware of the inclined hangers and their good aspects. And also the neighborhood, they were also informed. So we were kind of stuck in a situation where we had to, from a political point of view, use the inclined hangers and the problems that came with those. So we had a design session, a brainstorm session with the architects, and a few solutions or alternatives came. One of the alternatives was to make the hangers more of a zigzag pattern than crossing, like you can see on the Humber Bridge. This solved the clashing hanger problem, but not so much the going slack of the hangers, because it was still a bit of a problem. One of the solutions we finally adopted was to remove all the clashing hangers, which would go the other way, and have the V-shaped pattern in the middle where there were no clashes, and only a sort of fan on the outside. This was still not solving the going slack of the hangers, so we had to increase the hanger spacing. So the hangers by themselves would carry more dead load off the deck, and therefore have enough tension in them to not lose it all at the time. This would also mean that your deck would have made a bit longer spans at the time as well. So pushing us a bit out of the comfort zone in the deck design. That was a bit of a problem at the end, and a lot of stressful days. It's a bit difficult because it takes me 6 hours to get the drawing, make the model, do the form finding, and calculate if they're going to lose all their stress or not, while the architect can spit out suggestions and alternatives in 6 minutes. It's a bit of a problem. This is the final design as is. They hopefully start building it in half a year. The contractor is now busy with the design as well. So it's quite good. There's another project, a arch bridge in Zuidhoorn, a small city, town in the north of the Netherlands. A very architectural design, and we were asked by a steel contractor to join them in a design and construct bid. So we had to do a lot of calculations and sums to make sure we get the amount of steel correct and get a good price in, and able to win the project and then actually build it. But most engineers with a good eye, they get nervous when they see this picture. They say, oh, the top of the arch, their plates are doubly bent. That's a big no-go in engineering terms, to bend plates in 2 ways. It's really hard to do, really expensive, and generally not something you want. However, the architect who designed this bridge knew not to use doubly bent plates, so technically they're not all doubly bent. None of them are. The design has been defined in a few ways. Basically, from the side view, there are two arches, two circles with a defined radius. And from the cross section, you can see the ellipse shape, both on the inside and on the outside, making the cross section in the top like this. Well, this is the ellipse, and they're not actually double bent plates. You can see from the 3D sketch here, it's an intersection, so all plates are either the ellipse form or the arc, but none of them are double bent. So it's really hard to have this discussion. Every time you ask someone about a question, you show them the design, and they say, "Yeah, doubly bent." No, it's not. Close, but yeah, but it's it looks quite nice, but difficult designs, difficult details in designs everywhere. And it was quite interesting to see during the design process that some choices made by the architects have such an impact later on. In the Netherlands, we love bowstring arches. We do. Because, as I said before, we have really bad soils, so we don't really want to do these kinds of foundations. They're usually really expensive because you have to make a lot of piles and really deep. Well, most of the examples of these arches you've seen before today, they are between big mountains or valleys, making these foundations really easy to make compared to the sort of soup we live on. So we really wanted to make these bowstring arch, but we couldn't. The legs of the arch, they were defined by the architect as well. So if you make it to be outward, so if you make it a bowstring arch, it will be just a vertical force right on top of here, and it will create a moment between the end of the leg and the foundation, which was too big to make a difference. The foundation would be really expensive yet again, just because of the moment. So that was quite of a big problem to solve, and to have a big discussion with the people who did the foundations to make sure that all the designs were matching and that there was a final price which was economical. The other thing that's a bit of a weird aspect is that the side spans are actually quite a lot longer than all the intermediate spans between the hangers. So the dimension of your main girder in the middle is not based on the bit in the arch, it's actually determined by the bit on the outside. So that was a bit of a difficult thing to solve and to optimize your design. And finally, because of their curved plates, all the stiffeners that have to go inside are really expensive. Usually these are typical cross sections, so there's a thinner web and bigger flanges. And there are stiffeners in there and diaphragms. If these plates are bent, these stiffeners are hard to make. And because the shape is constantly changing, every stiffener in this bridge is a one-off stiffener. That will mean that every stiffener has to be drawn to scale, made to measure, and then have to be fitted. And that's a really expensive thing. So we had to talk a lot with the steel contractor to determine how they want to make the details, to make sure that it was going to be a difficult job, but that it was doable for a budget, even though this is not a cheap bridge. This is quite an expensive one. Next problem, multi-span cable systems. I always really like large bridges. I find bridges interesting. The picture is actually not really a multi-span cable system because it's multiple bridges connected to each other. There's an intermediate support here and over there as well. But for example, the fourth replacement crossing, or the Queensferry crossing in Edinburgh they're currently constructing, that is a multi-span cable system. It's a really nice bridge and a really cool site. If it's finished, there will be 3 centuries of bridges at one location. The old rail bridge built in 1890, the old suspension bridge built in 1960, and this one, which is I think planned to complete in 2017. So when it's finished, it will be a really good site. But at the time, it's still under construction. Also really interesting. The fourth replacement crossing is almost 3 kilometers long and with the longest span of 650 meters. And as you can see in this picture, it has 2 main spans, and that has some problems. Usually in symmetrical cable stay bridges, you balance the dead load, and then there's the problem of the live load, the cars being on one side and not on the other side, making the whole thing want to topple over. The easy solution is to connect these things to the ground with a tie down, making sure the whole thing is balanced when there's loading in the middle. However, if you have 2 spans and one span is loaded, you're actually lifting up the second span, making the deflections very large, and the pylon in the middle want to fall over. That's something, there's quite a lot of different ways to solve it, and depending on the situation, some options are more or less valid. The option they chose was to overlap the cable planes. I heard they say it in Spanish at the first presentation, so I don't actually know what he said, but saw it coming by. It's really simple. The middle bit is carried only by pylon B, and the overlapping bits are carried half by pylon A and half by pylon B, and here half and half as well. If one side is loaded, in this example, it will still be equally distributed between pylons B and C, but on the other hand, pylon B will carry a larger portion of the shared weight in the middle, thus keeping the pylon stable as well. But that's not the only solution. Just like many things, there's multiple solutions, and there has to be made a choice to see what solution is the best fit. You could actually string multiple bridges together, having an intermediate support to tie the whole thing down. You can also make a cable at the top to make sure the pylons in the middle don't fall over, or connect the top of the pylon towards the base of the next one. Or as you see in the bottom picture, overlapping cable planes. One option you don't see here is that you can also make the pylon very stiff enough to make sure that they don't bend. Some options you see here is in Hong Kong, where they actually made the cable from the top to the next pylon. And here in Greece, they made the pylons really stiff. This is not something, well, it is really impressive, but it's not really as aesthetic as some might say. However, this is in an earthquake zone, and this is a very good solution for seismic problems. Some more pictures. These are both in Japan. Well, the top one is actually not a multi-span because there's a tie down in the middle, and the bottom one is, it's a double suspension bridge with a stiffer middle pylon to make sure that they all balance out. After they solved the stability of the middle pylon, they were eager to jump to the next choice, the shape of the pylons. And there's lots of options, and you see them around the world with all different kinds of varieties and shapes and sizes. But as there's always pros and cons for each tower. For this case, the foundations were actually the main factor. As you can see on the left side, there's a really small footprint, thus making the foundation requirements a lot smaller, while on the total right there's a really big footprint, and that would mean you would require a bigger foundation. As you can see here, there's 2 foundations which are quite deep in the water, and they had to pour a lot of concrete to make those. I think they were 15 days straight of pouring concrete to make the foundation on this side. So quite a lot of concrete, and that's with the small foundation. But as in many things, many bridge designs, it's a good thing to adapt your solution to the situation. There's actually an island in the middle of the Forth, and they built a tiny lighthouse on top of it, because when it's high water, you don't see the island, and ships hit the island. But now they chose to make the pylon, the middle pylon, exactly on the island, thus reducing the need of the lighthouse. But also the foundation is easier to make. This is an asymmetrical cable stay bridge, the Erasmusbrug in Rotterdam, near the port. I quite like the bridge. I'm not really a big fan of the city, but that's a different story. But it's really nice, and it's gotten a lot of fame for its shape. But the shape itself is not decided by the architect. It's a technical solution. The architect preferred a straight pylon at this time, and the hangers more in a harp configuration than a fan. But that will make the bending moments in the pylon quite big and require the pylon to be very chunky. So the engineers decided to make a kink in the pylon and move the cables up, reducing the moments in the pylon and therefore making it more slender. You also see the big anchor cable because it's asymmetric. It wants to topple into the river. And yet again, in the Netherlands, we have bad soil. So these things are quite expensive to make, the big foundation. Tension piles are expensive and has to be quite long, and to make sure you have enough weight is also usually a bit difficult. However, here they also made use of the situation because there's a bascule bridge on the side. It's in the seaport, so there has to be quite big ships passing through every once in a while. So there's a big bascule bridge for the tall ships, which means a really chunky bascule basement with a lot of concrete and a really heavy bridge, making it a very good counterweight, solving your problem of your backstays while using the stuff at hand. Just after it opened, actually, it got in the news. It's usually a bad sign when your bridge gets into the news. There was a wet galloping of the hangers, the cables. When there was rain, which happens quite a lot in the Netherlands, and it was windy, there were droplets on the cables, and the wind would move the droplets and thus moving the cables as well. Solution is quite easy. You add either a string on the outside of your cable or some other pattern, making the droplets fall off and making it better aerodynamically. So that's why you see a lot of these things on newer bridges. However, at the time they just fitted dampers between the cables and the deck to make sure the problem was solved. The solution of the kink in the pylon, that's a solution you see quite often nowadays. In Dublin, for example, and you also see the same thing in Valencia. But it's all design choices. You don't have to. There's just consequences. And knowing what kind of consequences there are to your decisions is a good thing to know, because you don't have to have a backstay. You can also make the pylon really, really big. It's all a choice. So if you know what you're doing, you can do what you want. Thank you for your attention.